physicists have discovered a remarkable semimetal material that they say could pave the way for an entirely new area of physics. The new type of quantum material, known as Weyl fermions, were spotted during dual studies in Austria and the US. As researchers in one location were measuring its properties, the team across the ocean were theorizing how it could exist. The quasiparticles are the result of interactions between many particles, which causes them to move extremely slowly, about 3 millionth of the speed of light, despite having zero mass. This could one day prove useful for quantum computers and could even revolutionize electronics, the researchers say, as the system can conduct electrical current with almost no loss. These quasi-particles in a solid state behave somewhat like water in a wave, the researchers explain, where the movement of many water molecules drives the whole. The interconnected nature of the Weyl particles in the strongly correlated electron system means they also have extraordinary properties. This could mean high-temperature superconductivity and new kinds of phase transitions. In the solid state, the researchers found that the fermions move at less than 1,000 meters per second, or roughly 3 millionths the speed of light in a vacuum. Researchers say the discovery could one day prove useful for quantum computers and could even revolutionize electronics, as the system can conduct electrical current with almost no loss. Weyl fermions were first measured back in 2015, nearly a century after they were first predicted. Now, researchers from the Vienna University of Technology have successfully detected these particles in strongly correlated electron systems. By the laws of relativity, free particles with zero mass should spread at the speed of light. But the Weyl fermions are not free particles. Instead, they're what's known as quasiparticles in a solid state, meaning they come about as a result of interactions between electrons. These quasiparticles in a solid state behave somewhat like water in a wave, the researchers explain, where the movement of many water molecules drives the whole. Quasiparticles are not particles in the conventional sense, but rather excitations of a system consisting of many interacting particles, says Professor Silke Bühler-Paschen from the Institute of Solid-State Physics at TU Wien. The interconnected nature of the Weyl particles in the strongly correlated electron system means they also have extraordinary properties. This could mean high-temperature superconductivity and new kinds of phase transitions. So it was astonishing for us to detect Weyl fermions with a mass of zero in this particular type of material. In the solid state, the researchers found that the fermions move at less than 1,000 meters per second, or roughly 3 millionths the speed of light in a vacuum. Even though our Weyl fermions have no mass, their speed is extremely low, says Bühler-Paschen. As such, they are even slower than phonons, the analog to the water wave in the solid state, and this makes them detectable in our experiment. In parallel studies, researchers at TU Wien measured the properties of the remarkable material as the team at Rice University conducted theoretical investigations. Combined, the experiment and theory allowed for better understanding of the newly discovered effect. And the researchers say there are a number of things that make it extraordinary. Even if Weyl fermions were initially found in other materials, it is much easier to control the effect in our strongly correlated materials, says Silke Bühler-Paschen. Due to their low energy, it is significantly easier to influence them using parameters such as pressure or an external magnetic field. Eventually, the particles could be used in quantum computers or for more efficient electronics.